So good morning. Hope you have a good first day. So I had some homework for you yesterday. Did you do that? Anybody come up with any design of a turbine? You did? Okay. Can I have a look? Yeah, bring it here. Oh, we did some calculation also. Okay, excellent. Okay, okay, that's good. Bevel gear. That's very good. Yeah, that's very good. Complete generator. Excellent. Excellent. Okay, so I saw three of the design, and all the design actually went for uh, axial flow design with a bevel gear to transmit power into a vertical shaft, and then their motor is outside water, okay, on a float, and the float is like a boat type, right? That you came up with design. Excellent. Okay. So today we are going to talk about some of the technologies and innovation on hydrokinetic turbine and some of the design tool, software design tool available for make the design process easier, faster, more uh, more parameter you can study in within a short time. So that type of analysis we are going to do today. Uh, First of all, going back to what is hydrokinetic turbine, that's the definition that we need to remember. Is a device to generate electricity by harnessing kinetic energy of flowing water. So that's the important thing. We are looking at extracting kinetic energy of flowing water, and that can be river, tides, or ocean current. So the same design that you are doing for river, you can put it in ocean where there is a ocean current going on, maybe near southern part of India, near tip of Chennai. Those places might have heavy ocean current, and there also you can use the same technology. And also some of the river goes into ocean, and where you have tide, there also you can put this type of turbine. One of the problem with the tide is that it's bidirectional. Okay, so your turbine, you have to be careful what type of turbine you put for bidirectional flow. So can you tell me, anybody, what type of turbine will be useful? What we have learned so far, what type of turbine will be useful for bidirectional flow? Where you have a tide, what type of turbine you can use? Anybody can answer that quickly? Bidirectional flow. Flow happening in both direction. Which type of turbine? Say again? Radial means vertical axis turbine. Huh? Helical turbine, yeah. Or, yeah, those type of vertical axis turbine, helical turbine you said will be very useful. There is a name for that, is a Darius and Savonius. I think there are two different type of turbine there. That can be used for bidirectional flow. Okay, but river, as we talked about, maybe unidirectional, ocean current, mostly unidirectional. So what is our objective at the end? Application. We are trying to get renewable energy generation. Okay, and off-grid power supply and reducing carbon emissions. So our objective at the end is to reduce carbon emissions. Okay, so remember that term. I will come back to that term in a minute. or further down my lecture, carbon emissions. Off-grid power, that's very important because maybe many of the remote community may not have electricity. But what I know in India, maybe almost 100% is electrified. Every community has got electricity. You can correct me. Is that true? Like 100% is electrification done in India? Huh? Yeah, yeah, everywhere. Yeah. But say again, 90%. I think more than that, maybe almost 100%. Even if you go to remote community, yeah, they have electricity. Yeah, maybe solar power somewhere, if it is a very remote, maybe solar energy kind of thing. But again, this is an additional addition to have renewable energy, because last time I looked at certain percentage, very large community actually live along the river, along the river. Okay, most of the town, city is grown up along the river. Okay, so if you can have this type of supply, which is kind of renewable energy at the source, that are very useful. Okay. So as I talked about, there are two type of turbine we are looking at. One is horizontal axis turbine and one is vertical axis turbine. So if I stop here and ask you, what is your preference? Which type of, if I tell you, okay, let's design a turbine. So which will be your preference? Can I have a show of hand? Who will be designing horizontal axis turbine and who will be designing vertical axis turbine? Can I have a show of hand? Horizontal axis turbine. Only 1, 2, 3. And vertical axis turbine? Okay, you want to decide later after doing all sorts of analysis. But you may have a personal preference kind of thing, right? Like Mahesh said, he's looking for horizontal axis turbine, and you also said horizontal axis turbine, but nobody for vertical axis turbine. Yeah, I will go for vertical axis turbine because it's a bidirectional, number one, and it is also, you can put the generator and thing outside the water and things like that. Okay. Anyway, so let's move on to what are the key challenges, key innovation we did to make this turbine happen, to make this turbine happen. So one of the key innovation we need is material, advanced material for durability and efficiency. Okay, so we need to look at material science and come up with lightweight, non-corrosive material that can last for a long time and give you good efficiency at the same time. So when I talk about efficiency, let's think about we put a blade somewhere, and that has got, why we are talking about material. So you have a, theoretically we know we can create a turbine, we can put it in water, but we know that water has got lot of debris, okay, coming in. That debris can hit the blade. So in that case, how long the blade will last? What type of material you need? Some of the debris can tangle up in the blade. So what you can do? Or if you have fish coming in, so fish can strike blade, okay? Yes, you can use net, yeah, yes. So that is the technique you need to think about in terms of material or in terms of some guarding mechanism. Okay, so think about this type of efficiency. If you have water mixed with mud and things like that, muddy water, then what type of material you need for that type of blade? Okay, so you have to think about local context and efficiency. So in most of the time, what happens in lab, you get very good result in laboratory. But when you scale it up and we install it, then we may not get the results that we anticipated. Okay, so you have to look at local conditions. So blade design and optimization, that's uh, another area. So blade design, we can start off with very simple blade design. Okay, and then we can change it, we can optimize it, we can improve it, and we can come up with a optimized design. And these days we can use what you call uh, genetic algorithm or machine learning, those type of advanced technique to optimize the blade profile. Okay, then you have to think about mooring and anchoring system. As we talked about that before, we don't think about how we can have this anchoring and mooring system and how that interact with fluid and how that can change the whole dynamics of the flow. And also we need to look at power takeoff systems, okay, generator and electrical control and things like that, how you integrate with the whole system. And if you run it in parallel, say we have a system where you have hydrokinetic turbines plus solar energy, because hydrokinetic turbine runs over 24 hours, right? If the water is flowing, you can generate electricity. While solar energy, you are producing maybe 6, 7 hours, 8 hours. So if you have two different systems in a grid, how you balance those and how you control those mechanisms, that is very important, because to my mind, none of the solar renewable energy will work alone. Okay, you have to have a combination of different type of renewable energy, and those are intermittent, those are not continuous. So how you balance the grid, that is also a very important aspect. Though all of you, I think, is from mechanical engineering background, so we don't think about this thing, power takeoff system, but you have to work with the power takeoff system also. So again, when you think about research, you think about innovation. I talked about innovation before extensively. I also talk about collaboration and multidisciplinary research. So when it becomes more and more complex, you cannot do the research yourself. You have to combine with other researcher to look at the whole picture as a multidisciplinary aspect. Okay, so you may not be expert in power takeoff, but you need to have little bit of knowledge there. What are the other innovation coming? Modular design and scalable design. So the design that can be scaled up from 5 kilowatt to 10 to 20 kilowatt, those type of thing. So that scalable is very important in terms of designing. And modular design, so that's help with manufacturing process. Okay, so you can build it parts by parts, and then you can join it together. That's what we call modular design. Okay, you can make most of the turbine is actually made parts by parts, and then you can add it together. Fish-friendly turbine technology. That's very important. Can anybody give me any ideas about how we can make fish friendly? One of your friends say net. Anything else you can think of? Fish friendly turbine technology. Okay, can you do something on the blade? So the fish coming and hitting the blade and then survive basically. Say again? You want to do flexible blade? Yeah. Huh? Yes, yes. That's good. That's good. So maybe soft blade or soft in the front kind of thing. Yeah. So it doesn't, fish is not, if it is impacted, it doesn't create any problem. You said net. Anything else? Say again? Okay. So you think about fish-friendly turbine technology. Okay, think about that. I will come back to that later. An adaptive control system for variable flow conditions. If your flow fluctuate between 2 meter to 2.5 meter to 3 meter, then back to 2 meter, then again 2.1 meter, if the flow changes continuously, so you have to have a adaptive control system, so you get the maximum efficiency. So you get the maximum efficiency when your uh, tip speed ratio is fixed, constant. So if you want to keep your tip speed ratio constant, you have to have a control system that will continuously change either torque or pitch angle to give you the maximum efficiency all the time whenever the uh, flow condition changes. Yeah. And thus again I said integration with energy storage system. So what are the energy storage system that we can think of? And it has to combine with other renewable energy sources also. Okay. And that is the challenge. What is the main challenge of renewable energy system is actually energy storage. So can anybody tell me what type of energy storage system you can think of? Batteries for the time being. What else? You can have lot of other system, mechanical system, and also chemical system. So you have electricity generated. If you don't need the electricity, you can run a electrolyzer to produce hydrogen and keep hydrogen in a tank. And when you need electricity, you take this hydrogen, put it through fuel cell and generate back the electricity. Okay, the same concept as you say about battery. Okay, hydrogen can be chemical changes and medium of energy storage. Mechanical system you can have, or also electrical system, other type of system you can have, compressed air storage, that type of system you can build. So a lot of energy storage can be done. The best one you said, or the simplest one is battery. So these are the challenges with hydrokinetic turbine and innovation that we need to look at. So what is the future trend and direction? So emerging technologies, biomimicry, AI-driven optimization, as I say, blade design optimization or control system optimization. Even you want to combine different renewable source and how you balance those, that is using AI-driven optimization. Biomimicry, blade design. Anybody has any example of biomimicry blade design? Yes. Aeroplane base, yes, yes, good. Helicopters, yes. Humpback, well, yes. Okay, so I will come to, I will show you one example. So these are the design you can look at. Hybrid system, that's interesting. Potential for hybrid system. Wind plus hydrokinetic energy. How is that works? Yeah, so you have a structure. You put hydrokinetic turbine in water, and on the top you put wind turbines. If you have wind and water both at the same location, so you can do that, yeah, and generate double the electricity from the same structure. Okay, hybrid system and role in achieving global renewable energy targets. So that's what our research is all about. Whatever we do, activity, why you are spending so much time, so much energy, research money, your time, my time. Why is that? At the end of the day, we want to achieve a global renewable energy targets. So we have a target. I know for global target, you want to keep the temperature below 2 degrees Celsius or 1.5 degrees Celsius at the end of this millennium, right? Also, like in Scotland, we have a target of achieving net zero emission by 2045. And this is went through the parliament, it's a law, so you have to do it. You have no other options. Similarly, UK has a target of achieving net zero emission by 2050, 5 years after Scotland target. Okay, because Scotland is a small country and it has got lot of oil and gas to start off with, but now they have lot of offshore wind energy because it's very windy, very cold country, but very windy also. So there are two energy focus in Scotland. One is offshore wind and one is hydrogen, because offshore wind, the storage you talk about, battery, but battery is one thing, but you then use that offshore wind to turn excess energy into hydrogen and then use that hydrogen later. And a lot of hydrogen related project going on around Scotland. Okay, so at the end of the day, we have hydrokinetic turbine, we can use wind energy together, and then we can use hydrogen energy storage, and you have to achieve global renewable energy target at the end. So again, my advice, those who are coming into future, into job market and thinking about research and things like that, is to look at what are the big challenges you are facing, maybe in your day-to-day life. What are the big challenges you are facing, or your country is facing, or your surrounding is facing, and then think about what you can do to solve those problems. So achieving global energy target is a big thing, okay, and that will continue into your future up to 2050, 2060, 2070. So these are the job that you can look at into the future. So hydrokinetic and wind combined together. So if anybody wants to do research project after Mahesh, after he's completed his PhD, he wants to advise and continue his project, they can combine these two together, right? And come up with a better solution. Hydrokinetic and wind. And work in multidisciplinary area and work in collaboration with others. Okay, you don't stay in your own domain, and that will make more of your work more interesting. So now I'm going to talk a little bit about some of the software that is available and that can be used for generating so different type of simulation and things like that. The first software I'm going to talk about is Delft 3D Flow. This is a river flow simulation. Okay, and it is available for free, so you can download it. What it does is simulate whole river system. If you don't have the data, if you know the outline of your river from somewhere, I don't know where, and if you have some initial condition, river condition, then you can say that this will be the velocity within the river, and there will be turbulence, vortices and things like that. So if you look at those corners here, that will be vortex flow and things like that, but you can do the whole river simulation using the software called Delft 3D Flow, and it's available for free. Okay, if you have the data in your river, that's fine. If not, use that to simulate the flow, maybe in Ganges, maybe in other river we talked about, Brahmaputra and things like that. Yeah, width of river. Yeah, x, y, length and width. Okay, and then you can say the velocity here is maximum 2 meters per second. Maybe this is a good place to put your hydrokinetic turbine. If you want to put it here, sorry, if I can go back to my laser pointer. This may be a good place to put your hydrokinetic turbines because they have the high velocity of 2 meters per second. If I tell you, okay, put your hydrokinetic turbine here, is that a good location? No, sir. So that type of simulation is important to find out the location. Okay, if you don't have the data, you can have this type of river data in other source also, that I will discuss a little bit in a minute. But this is the software, as I said. If you are interested, you can download and run it. Another software freely available is HARP Opt. It's a very good software. This is developed for wind energy, but it can also be used for hydrokinetic turbine blade design, and that is also available free from this website. Okay, so if you use that software, what is the output you get? So you get, if you have different flow speed, say you started from 0.5 meter per second up to 1.5 meter per second, this is the range. So what it does, first of all, it will create a blade profile. So if you have the chord length at different radius, so if your blade start at a blade is 10 meter radius here, so you can see the chord length. This gives you chord length. Chord length is 1.6 meter at the beginning, and then if you go to the tip of the blade, chord length gradually reduced to 0.2 meter. So you started off with a very what do you call long, how do you say, it's not wide blade, is a 1.6 meter, and as you go to the tip away from the center towards the end, this is horizontal axis, right, toward the end, so your blade chord becomes smaller and only 0.2 meter, 1.6 meter to 2 meter. Sorry, the blue line, 1.6 meter to 0.2 meter. And this is the twist angle. So blade is not like this. Blade is not like this. You have to twist different location at a different angle. So you start off with a twist of, what is that, 30 degree, and then gradually you reduce the twist up to almost 0 degree. So it becoming like this. And in the beginning, it twisted. I cannot twist my hand, right? So, but the blade, it twisted. You got the idea, right? If I have a paper, I could have shown you. What is a twist? You want to demonstrate, right? You demonstrate that, how the twist works. Yes, exactly. Yeah. Yes. Twisted blade. Okay. And this software will do that. HARP Opti. Understand? And if you want to, then once you get the blade, you know the velocity, and each of the blade will have a lift coefficient and drag coefficient for each of these angle. Once you get the lift and drag coefficient, you should be able to calculate your power. So let's follow the power. At velocity of 0.5 or below that, power is 0. It's not rotating. You need a certain amount of velocity to start turning, and that is goes up and up to this point. This is your rated power. So your rated power is 250 kilowatt, maybe. Yeah? Let's take this number. 250 kilowatt is your rated power, and your rated speed is 1.4 meter per second. After that, whatever the speed goes up, you control the turbine, you don't extract more power. You fixed your power, maximum power at a rated power. Other than you start to rotate violently and it will may destroy the motor, turbine, everything. Generator and gearbox. Okay. So you fixed it. If the velocity is too high, you actually stopped it sometime to protect it, right? You don't run it. If the velocity becomes 5 meter per second, 10 meter per second, then you don't run it. Okay. So there is a rated speed, rated power. And if you look at the coefficient of power coefficient we talked about before, which is a substitute for efficiency basically, and that value reach up to 0.5 at a speed of 1, but it has got a wide range. So this blade is very good. So it has got a wide range of power coefficient, wide range of velocity. You get a similar power coefficient 0.4 to 0.5. Okay, so maximum limit. Do you remember anybody? What is the maximum limit? 0.59. Yeah. Yeah. So it's below efficiency, right? Okay, 0.6, maybe 0.59. So that's the maximum theoretical power. We call it a base law. Okay. So this software is generating this output. Okay. HARP. Then there is another software called Q-Blade that is used to design this type of blade profile. A similar concept, where you have HARP optimization and also Q-Blade. You give your conditions, your things, and that will design the blade. Again, you can see that here your chord length reduces. Okay, this is the maximum chord length. As you go along, chord length reduces, and there is a twist here, and highest twist here, and the twist angle get reduced. Okay, you can have blade without twist also to start off with. If you want to do your design and play around, okay, let's forget about the twist, make a plain blade and run it and see what is the CP value you get. What is the CP value you get? Then gradually you optimize the blade. You can do it many different way when you are learning. So Q-Blade is another software that is available for designing hydrokinetic turbine. It's very similar to HARP. Homer, another software. This is work to designing lot of things it does. So it is actually a very good software. It has got a free element, and also you have to some part you have to buy it. Why it is I am giving you that. It's not exclusively for designing hydrokinetic turbine. It's not exclusively used for designing hydrokinetic turbine. It is to combine your solar energy here, your hydrokinetic turbine here, your wind energy here, combining this, then is go into AC power, different type of converter, electrical load, different type of uses, DC, then you come into battery. You talked about electrolyzer. I talk about hydrogen generation as a medium of storage, hydrogen pipeline, hydrogen storage tank, hydrogen load. So all the whole system integration can be simulated within this software. Okay, so if you want to do it individually, you have to learn power output of this, power output of this. Of course, you need to learn. You need to learn the theory, all the equations. That's basic knowledge you need to have. But then if you want to write a computer code based on all those systems, it may take 1 year. And then you have to debug the code, see how it is working correctly or not. It's a long process, right? So to speed up that process, you can use this type of software that will optimize the whole system. For example, you have 5 kilowatt of, here is a 20 kilowatt, 40 kilowatt of PV and 10 kilowatt of wind energy, these three systems. And then you have a load profile and things like that. Then I say, how big is the hydrogen storage needed if we want to store 20% of the power? So that will then calculate that hydrogen tank we need is 100 kg. Okay, and if you want to calculate what is the size of electrolyzer needed for 100 kg of hydrogen tank, then it can calculate electrolyzer size of 20 kilowatt and battery of 100 kilowatt hour. So these, all the calculation can be done within Homer software. You just build the system, give the input, your input here, your output is the electrical load profile. You say, I want to store this amount of energy at different time and things like that, and that will calculate whole thing. But in order to use that software, you need to know theory of these, equations of these. You already showed me some of the calculation. Those are the basic theory you need to know before you can move on to using this type of software. This is for optimization of power system, sizing. It can size the hydrogen tank, electrolyzer, battery. It can analyze microgrid system, and most importantly, we talked about cost and levelized cost of electricity generation. It can calculate, and that is the most important part. Any system you build in, if this levelized cost of electricity generation is more than what we have now, nobody will actually buy from you, and it will not be commercially viable. So important thing is to be able to calculate this one. But again, if you want to calculate that manually, it takes long time, right? And you know basic theory, what is levelized cost of electricity. Once you know the basic theory, you use type of software that give you the answer. But if you use that software blindly without knowing different meaning of different term, if you and knowing the theory, if you use those software blindly, that then you, of course, the result will not make much sense and you will not be interpreted. So the advice will be to learn the theory, then if the software is there to help you to come up with. Another important part we talked about is, if I go back and I told you to remember carbon emission. That, how do you achieve that? How do you know it's reducing carbon dioxide emission? How do you know that? To do that, we call it life cycle analysis. So if you have this turbine, it will last maybe 25 years, right? And to make the turbine itself, you need to have materials, you need to have electrical generator, you need to have what else? Cable. So for example, let's think about electrical generator that we have. You bought it from Germany, okay, and that is exported from Germany to here, and from here you take it to a remote area in Assam to put it here there. So if you trace the whole path of how much carbon dioxide emission happens to bring it from Germany to your location, you understand? Then to make the blade and things, you are making your blade somewhere in, say, Pune, and from there you are transporting it to your Assam. Okay. Again, the carbon dioxide emission happening due to this transportation. Raw material. The raw material is coming from maybe another country, South Africa or somewhere. That, what is the emission happening? So whole life cycle analysis is important. How you do that? Life cycle analysis. If you want to trace that manually and pick up the data manually from Google search, from book, from journal article, and try to calculate how much is the carbon emission happening to build your turbine, to use it to generate electricity for 25 years. You have to add everything, maintenance within that. If you add everything, then how do you do that? If you have to do it manually, it's a daunting process. Data itself will be very difficult. Finding data, a generator from one source to another source. So that is a big challenge. And to make the big challenge easier for you, we have a software. Oh, I didn't write the name. It's strange. We have a software freely available again, and it is called Open LCA, Life Cycle Analysis. Open LCA. Very good software. Okay. It's very, very important that when you design a system, your hydrokinetic turbine, you use it for 25 years, you need to know how much is the emission happening over the whole process of your lifetime. And if that process doesn't reduce your carbon dioxide emission, you actually add to carbon dioxide emission, then you don't get the benefit. Yeah? You understand? So any new thing you bring in, use it, you need to do a whole life cycle analysis, and there is a software called Open LCA. And as I said, the data, where you will get this data? Data is inbuilt here. You just say, I am using this motor, origin from here, transporting to there, and it will calculate automatically. You build up your system like this, and that will give you what is the emission of carbon dioxide during the whole process. You understand? So Open LCA. There are other life cycle analysis software which can be expensive, but this is a very nice software. And as I said, maybe you use yourself or you collaborate with your friend, you do a research on turbine blade design, somebody doing research on power emission or power generation, somebody then doing research on life cycle analysis. You combine 3 PhD work or 3 research work, 3 undergraduate project together, okay, and then you get a complete outcome. That's very important. You need to have a multidisciplinary approach to any project, and your thinking will be broader. Yeah, do I make sense? Yeah. Okay, so life cycle analysis. So probably I will give you a break now and then move on to next set of talk in a minute. Okay, so let's stop here. So I think you are all back, so we'll make a start now. Let's make a start. So now we'll talk about little bit about more software as we're keeping the theme going. So let's look at some of the commercial software, some of the open source software. So what is the difference between commercial software and freely available software? Commercial software, you have to pay for licenses. It's a very expensive actually. But the one added benefit you get is that you get technical support from them, and also you get manual and a lot of case study manual and training and things like that. So some of the open source documentation is not there. You have to learn yourself, and the learning process is quite difficult because you may not have the proper documentation for using free software. So first of all, I'm going to talk about ANSYS Fluent or CFX. Similar to that is Star CCM Plus, and then there are many other commercial software. It is called computational fluid dynamics. So whatever fluid is flowing, we simulate it in computer. This is the branch of fluid dynamics that came into existence after the advent of computer. When the computer came, then this computational fluid dynamics became a very big thing. This is for simulating fluid flow, turbulence, pressure distribution around hydrokinetic turbine blades. So if you have a blade and if you are interested, blade is rotating, you want to look at more in details how the flow dynamics happening, then you need to use this type of software called the computational fluid dynamics. Okay, this is used for optimizing blade design, analyzing hydrodynamic performance. These are the two things, but this blade design can be done in other software also, but there are many other benefit of computational fluid dynamics. So can anybody wants who has experience in computational fluid dynamics, because whole day today after me we'll be spending time on computational fluid dynamics in details. But before go there, can anybody, those who have experience in computational fluid dynamics, can say what is the advantage of using this computational fluid dynamics for hydrokinetic turbine blade design or analysis? Because I have already shown you how you can design the blade using the other software, and I will show you another software in details towards the end of my lecture. But can anybody tell me what's the benefit of this? Yeah. Yes. Yes. Yeah. Okay. Yeah. Anyone else who wants to? Yeah, we can reduce the experimental cost by using software, right? But what is the added benefit we get? Say, for example, we want to optimize a blade design. And to optimize a blade design, we can use this type of software, which is called HARP Opti, and this is actually blade design. That's the main thing. You take a blade, you need to find out what is the chord length at different radius and what is the twist angle at different radius. If you know that, you can then put it in a CAD design software and this will be your blade. Then you can do a 3D printing, or you can take it to your manufacturer and he will manufacture this type of blade and then you put it in water. But CFD must have some other benefit on top of blade design. Okay, so you can have many other parameters that you can analyze. Also, I want to ask you. So water is coming like this, blade is rotating like that. So what happens after blade? What happens to the flow after blade? Yeah. Yes. Yeah. Yeah. Yes. What is the last point you say? In what to prevent swelling effect. So what happens? Let's rotating like this, right? Those who are in undergraduate, some of you are from undergraduate BTech, right? So what is happening is that blade is rotating like this, flow is coming this, and after blade, fluid start to flow like this. So let's take a fish. Fish is coming. If the blade is here, blade is rotating. What will happen to the fish after it goes through the blade? It will go round, churn itself. Okay? So that type of visualization you can do. And I will say, if you are doing CFD modeling, just release a fix in your CFD model. Yeah, some of you already have experience in CFD modeling, and those who don't have experience, we'll deal with that later today. Lot of work on CFD modeling, but that will be interesting exercise. You have your blade design, you run your CFD model, then you have a particle tracking option in this model. So let's release a particle representing fish and see what happened when that particle came, hit the blade, which direction it goes. Yeah, that will be interesting exercise. So a lot of things you can simulate in this type of computational fluid dynamics software. And this is ANSYS Fluent and CFX. These are the two prime one. Then you have StarCCM Plus or many other software. You need that. SolidWorks is actually one of the most useful. SolidWorks or Solid Edge or AutoCAD or whatever CAD soft CATIA, right? Whatever software you have for designing, that is actually more important than this one. So you need to create a 3D CAD design and modeling of hydrokinetic turbine component. So that's very important. So you can then create this type of this type of design from your CAD drawing, and then CAD drawing can be used for 3D printing. If you want to create a small size lab scale your turbine, or if you want to make it bigger, you have to give it to your manufacturer and they will work on that. So CAD design is important, SolidWorks. Detailed mechanical design and assemblies, that's the purpose. Once you have this SolidWorks design, you can actually put it in CFD modeling also and do the flow analysis. So this is a very important package to learn for turbine blade. Then MATLAB Simulink, that can be used for analysis of the performance. Okay, and that doesn't need your CFD simulation. It is a simpler version, and MATLAB Simulink can be used to have designing control, power generation, whole system integration, battery storage. All of the component can be built up in Simulink, and then you can analyze the whole system. Okay, that is a very important software. MATLAB Simulink. Anybody has experience with MATLAB? I think we teach it in our first year or second year. You use that here in first, second year. Maybe later down you will use that software. It's a very important software, especially Simulink part, where you just create a block, and then you can analyze a lot of whole system. You can have the turbine, you can have generator, you can have DC AC converter, inverter, converter, control mechanism, everything. I will talk about control mechanism further down in my lecture. So this is system level simulation and control algorithm development. Okay, you have to control the power, that is important. Q-blade, I talked about that before. Purpose, this is a specialized tool for blade design and performance analysis. So you see, there are a lot of simpler tools and lot of complex tools available. So these are for designing and optimization based on say base limit, lift coefficient, drag coefficient, and the simple equation that we looked at before. Blade, what is the theory we talked about? Blade element method. That's the heart of all those Q, blade, and other software. However, CFD itself doesn't design anything. It doesn't design anything. You have to design it using either Q-blade or some other software, and then put it here to do the simulation, to look at the flow situation. So that doesn't do the design yourself. You have to do that, but Q-blade does the designing for yourself. Okay, that's the difference. So that's why there are a lot of tools and software available. Let's look at some of the open source software which are freely available, open source. What is that? One is called Blender. It's widely used here, open source 3D modeling software. And this is Blender is equivalent to your SolidWorks. Okay, so it's a CAD model, Blender, and this is freely available. You can create a 3D model, animation of hydrokinetic turbines and things like that. Blender is one. OpenFOAM, anybody heard about OpenFOAM? And this is also a computational fluid dynamic software. This is freely available. You can download and use it. And if you become expert, that will replace whole of your ANSYS Fluent CFX. Okay, that flow simulation software called OpenFOAM. And this is I think there is a learning curve. It's not easy to learn OpenFOAM compared to ANSYS Fluent CFX, but you should be able to you get it freely. Yeah, and if you are interested in computer programming using simulation, things like that, OpenFOAM is the way to go. Okay, another software is Salome, and this is again a freely available CAD software. This is used for meshing also, and that can be used in conjunction with OpenFOAM. So that's also design software. Okay, this is your CAD package and this is your simulation package, OpenFOAM. Now another software is very important is QGIS. So what is GIS? GIS is a geographic information system. QGIS is an open source geographic information system. This is for site selection and resource assessment. Site selection and resource assessment. Okay, so let's look at used for mapping and analyzing potential installation site. Okay, where is that installation site that you want to put in? Okay, let's go back to a slide here. So this is that river simulation software, Delft 3D flow, and you can see this is your proper site here. QGIS is similar, but it's a mapping system. The actual data is collected, put it in a map. Have you seen Google Map? So in terms of Google Map, you put another layer, another layer, another layer, and then you can create a resource map, and that is what QGIS does. You take a map, river, on top of you put some other layer, put other layer. Now in the Google Map you can see the traffic, right? Where the traffic is red color or green color and things like that. That give you where is the traffic jam and things like that layer. Similar to that, this is QGIS is a software. You load the map of India first, suppose, and then you put where are the rivers. So rivers. Then in the river, you put where are the velocity of the river. You put another layer. Then another layer on the map. Then finally you can say where is the velocity range of 1 to 3 meters per second. So these are the location. Then you put even what you call kind of a model of hydrokinetic turbine on those locations. Then you create a big map, layer by layer. You create a map, and that map shows you what are the location of the appropriate hydrokinetic turbine. So I will try to show you after towards the end of this session one of the QGIS map. Yeah, so you start off with like a plane map, like a Google map. Then you put river map. Then you put velocity map of river. Then you identify the range of velocity. Then finally you put a picture of this hydrokinetic turbine within the map. Then you print out the map, give it to your policymaker or your designer, then you can say, okay, these are the location in India, these are the suitable place to put your turbine. Is that clear? That works QGIS. Okay, I will show you the map later. Okay, now let's look at some of the CFD simulation examples. Okay, because CFD simulation goes beyond what you can see in when you are running a turbine. So that's a very important tool to understand. When you design a blade, you put it in water, and then what happens. So let's look at a design of a blade type, which is Darius hydrokinetic turbine. So these are the three-bladed turbine. We are looking from the top. Three blade we have, 1, 2, 3. This is your one. This is your one. Similar to your one, right? Yeah. Yeah. So I just picked up randomly from latest journal publication, right? Oh, right. Similar concept, yeah. So this is a three-bladed design. Look at the three blade here, first of all. These are aerodynamic shape and these are rotating. So when you don't know what is happening, you can simulate the flow and see these are the peak point where the velocity is very high. It goes up to 5.2 meter per second here. Your velocity coming at 2 meter per second, but the blade is also rotating. So in the front, it experiencing is a very high velocity here, 5 meter per second. Below the blade, you have very low recirculation zone here and here. And this flow going in, then impacting this blade. So maybe this blade is not experiencing the type of flow that is needed to get a smooth torque and things like that. Then if you think about the blade is moving here and some other instant, we change the blade shape. So we have this type of blade, which is standard. And then I talked about innovation last time, right? Okay. Innovation is to come up with new ideas. So this is one of the example of innovation. You have a standard blade here. That we know. Now you think, okay, let's make some dimple here. If you think about golf ball, anybody has seen golf ball? Golf ball has a lot of dimple. Why there is dimple? To enhance turbulence and to reduce drag force basically. Minimize the flow separation or trigger the turbulence so that what we call a drag crisis. Drag crisis happened at a low velocity. So think about that one. Okay, we have a dimple in golf ball. So why don't we put some dimple here and see if you can have reduced flow separation that your friend talking about. So these are some of these. And then you can have a slot. And then you can have different type of slot at different location. Okay, in the front, in the back, and things like that on the blade. These are all for what you call controlling the flow, reduce flow separation. So a lot of technique is there. And then you look at simulate in the computer, and then you see the pressure profile. Where is the pressure? You can look on the blade very carefully. This is a positive pressure here, negative pressure here, and this type of dimple slot will create the different velocity profile and different pressure profile and try to manage the flow separation basically. And as a result, what you have? At the result, what you have? So if you look at our standard blade, which is blue color here, this one, standard blade here. And if you look at efficiency, it's about 40% or something like that here. And TSR, TP speed ratio, varies from 5 to 2, something like that here. This is the peak value. By changing modification on the blade, let's look at this one. What happened? By changing modification, you didn't actually improve. Rather, so not all the modification will make it better. So you made a modification and your performance goes down. You make other modification, its performance goes down further. Only in one case you can see its performance has gone up. So not lot of these changes will make you better performance. It can become worse performance also, but in one case you get a better performance. So in order to create 1, 2, 3, 4, 5, 6 different blade, you actually need to spend lot of time and money physically to put it, make it, and then put it in your either water tunnel or in a river, and you do the experiment and you see that it's not working. So that's a very time consuming, expensive. And this type of simulation you can do in a computer maybe within 2 months, 3 months, or maybe 6 months. Okay, so this type of simulation, it's a computer simulation without putting everything in a make it or build it or test it. Computer simulation will help you to decide which is the best design. And from there, you can take that design here. This is the best design. Take that design here, and then you manufacture that and use it. And you can look at all the pressure profile and velocity profile, everything using that type of simulation. So that's one way of changing the blade design to look at the performance. Okay, not angle of attack. We are not changing the angle of attack or twist angle. This is just creating surface modification, different type of slot, different type of dimple. You can, I think, create more dimple or things like that. Or vortex generator is the other word we used. On top of the blade, you can have vortex generator to influence the flow separation. You talked about flow separation, right? Yeah, so vortex generator will also help or mitigate against flow separation. Flow separation is, we want the make, so if you have a, those who are undergraduate student, flow separation means flow coming in here, we want the flow to stick with the wall and flow like this. But sometimes flow comes in here, hit here, and then separate out. So flow separation will create a lot of drag force, drag. We want lift, we don't want drag. In a blade, we want lift force, that gives you the power. And if it creates drag, we don't want that. So we have to prevent, we want flow to like this. We don't want flow to come here, hit it, and separate out. And to prevent that flow separation, you can have this type of dimple, slot, and things like that. And that improve your performance. Sometimes it improves, sometimes it may not. You see, these are the situation where it is not improving. Okay, let's look at another type of turbine design. This is physically, if I want to show physically, it's probably like this. Is that correct? Yeah, two hand, 2 cup, one, another cup, like this. That is rotating. Okay, so this type of blade design here, you see 1 cup, another cup. The key parameter here, looking at these two, SG and O here, and this blade again can be twisted. Okay, twisted blade, this type. Now this is biomimicry. So you look at the nature and environment and see what type of curve is there. And if you look at this, I guess this is a fruit, and this is a snail, and you look at the curve, is what you call Fibonacci circle structure, Fibonacci. So if you start off with here, this square, you start another square, another square, another square, another square, you break it down into square, 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 and then if you want to join those shape, and it create this type of natural curve. Okay, so if you have this curve I was talking about, you can turn into this type of Fibonacci curve. You can take any section from here. So this is your original curve, which is semicircle kind of thing, right? Semicircle, exactly. Uh, this curve, dotted line here, and then you turn into a Fibonacci circle, and see if the nature give you some clue to improve performance. If you, instead of having two semicircle like that, if you follow this shape as a natural shape like this Fibonacci circle, whether you get better performance or not. So after creating this type of geometry curve, what we do? Of course, we can make it, build it, and test it. Instead of doing that, we can also put it in computer simulation, and we can look at complete flow dynamics. So that looks at the pressure profile, high pressure here, low pressure here in one geometry, and then your pressure profile changes because you change your geometry. You have the location of pressure and the spread of the high pressure and low pressure zone changes, and the location changes, and it is rotating like that. Okay, and if you look at vorticity is the important parameter. Some of you already talked about. Vorticity means how the fluid is rotating. After the blade, when flow comes out from the tip of the blade here, it will start to rotate. And how this rotation happens and how you can control that vorticity can help you to give you better flow. Okay, so we want to reduce the vortex dynamics or vorticity, make the flow smooth, and this type of changes in design from complete semicircle to Fibonacci circle, which is following the nature. Then you can see the changes of flow dynamics happening at two different locations, two different angle from standard blade and Fibonacci blade and things like that. And finally, you can look at CP value, pressure coefficient or the efficiency, and this is your standard Savonius blade, and this is your Fibonacci blade, and you can see Fibonacci blade gives you a certain improvement of efficiency. Okay, so you can look at the nature also. As I said many times, if you are to innovate something, you need to look around yourself and look at your personal experience and look at what is happening surrounding you, and that will give you some help and clue to come up with your experience. So this is just a curve here, like this pattern curve, semicircle. If you cut this, you can make this type of turbine very easily. You take it, you split it in the middle, and then you attach it like that, you get your turbine. Yeah, and then the semicircle curve, you look at the nature and think about, okay, let's not have this, let's follow the nature and see if it improves or not. It may improve, may not improve, but in this case it shows that this type of blade shape design will improve the performance. Okay, that's how innovation happens. As I told you many times, you need to think about innovatively and think about just making some changes, what type of improvement you get. Okay, so that's the design part or software. Then I will demonstrate a software to design the blade now, running a software itself to demonstrate how you can come up with blade design. Okay, before that, can I ask you this one again? Think about, you have come up with your blade design that you did yesterday night, you showed me. Now you think about what we have done today. what type of innovation we talked about. We talked about following the nature. We talked about in the beginning, we talked about what we need. We need modular design. We need fish-friendly turbine technology. These are the two things we think about. Based on that, again, blade design and optimization, mooring system, based on that, and also give you some example of, this is one example of change of blade, another example here, but you don't need to follow those. Now think about, okay, you came up with your initial design yesterday I talked to you, and can I now think about and come up with any other changes in my design? Okay, that will be your exercise to think about, okay, I have this my standard blade design. I look at two innovation that we talked about, and we show you the output also. Some changes make it better, some changes doesn't make it better. And also here we show you follow the nature. So you can come up with any other blade design from this concept here. Okay. Now I'll show you some software that I showed you yesterday, but I am going through that software for blade design. So let me find that one. Okay, let me find this one first. Oh, you can see it, right? Good. So what I did is actually took the blade element theory and then wrote a Excel spreadsheet, because you are familiar with Excel spreadsheet, everybody, I think. Yeah, so you can use it for designing your blade. That's my whole idea. So I will share with you. You will get access to this spreadsheet, so you can use that to design a turbine. Okay, sorry, playing around. So what we have? We want to create a turbine with a power output of 746 watt. But our target is actually 5 kilowatt. So this is a very small turbine. Fluid density is 997 kg per meter cube. Velocity of water is 1.5 meter. Power coefficient is 0.4382. The blade you are using and the turbine design you have is a axial flow turbine is 0.4382. Power coefficient. You can make it 0.4 or 0.5. And the total efficiency of the system is 70%. So that means this 70% is from output of the electrical power. Okay, 70% electrical power. Yeah, and this is output at the electrical power level. Mechanical output will be more than this because of this efficiency kind of thing. You assume a blade number of 3. You can assume 4 or 5 if you want. And the blade you selected has a high lift coefficient 0.8 and very small drag. As your friend before said that in a blade we need high lift, small drag. So the aerofoil or hydrofoil that's selected, you have that. Okay. Now you also assume a tip speed ratio of 4. Okay. Or you can have 5, 6, you can change it. tip speed ratio. Angle of attack, to get the maximum lift here 0.8, you need to set the blade angle of attack of 0.5. If my blade is not rotating, like the flow is coming this way, hitting, we keep our blade like this, 0.5 degree. Assume it's not rotating, flow is coming, you get the maximum lift. But the problem is flow is coming and blade start to rotate, where you need to take into relative velocity. Is that clear? So blade is here, flow is coming here, fine. But then if your blade will start to move like this, then you have to consider relative velocity, and your angle of attack is no longer fixed. You need to twist like this handle to get the maximum uniform power output. Okay, so from the root of the blade, so this is my root here, and this is my tip, root to tip, I split into 10 sections. We can split into 20 sections also, but for simplified calculation, we split into 10 sections. And so the tip, the blade is 0.8 meter, I think, yeah, 0.8 meter radius, blade is 0.8 meter radius. So I split into 10 sections, each section has got 0.08 thickness. Rotational, what we need, okay, so since we know tip speed ratio and the velocity, we can calculate rotational speed omega of 13.952. This is the calculated number. We can calculate very easily. Okay. Now for each of these, so when we want to design the blade, what we need for each of these stations, each of the 10 sections, we need to find out chord length and chord length and twist angle. That's the main thing, chord length and twist angle. So for each of these locations, 0.08, 0.16, 0.24, up to 0.8. Two things we need to calculate. You said twist angle and chord length. So do that. First of all, you have to calculate relative velocity angle phi, and to calculate that number, this is 45 here, 32, 26. To do that, we use this formula here. This is the formula to calculate phi. Okay, so these are the angle. Then also you have to calculate induction factor, axial induction factor. How much is velocity, free stream velocity changes due to the presence of the blade. So that induction factor you have to calculate. The formula is given here, very straightforward. A, this is angular induction factor. Okay, and this is the chord length. So you put all those formula into Excel spreadsheet here for each section. So you calculate A, you calculate A prime, these are the formula here on the top. The twist angle is 40 degree. That's the main output you are looking for. And this is the angle. This is the twist angle. Where is the twist angle? And this is the chord length. These are the two important parameters. So you see the chord length 0.39 gradually reduced to 0.091 chord length. And this is the twist angle you have. Now this is any type of blade is a chord length. Now I take a blade aerofoil S822 aerofoil, and when you take aerofoil, these are represented by XC and YC. X divided by C is a non-dimensionalized by chord length, and so this is how X and Y value of a profile is given. We know the value of C at different location, so we can calculate actual X and Y at radius 0.089 near your wall. Okay, So this is the relative distance, relative size of the aerofoil. You can see this aerofoil is at the root, this big one is at the root, the small one is at the tip. We only calculated two locations, at the root, at the tip. So this aerofoil shape is at the root, this is at the tip. And this is actually needed to be twisted. I didn't plot the twist here, but how much it has to be twisted? It has to be twisted by 40 degree. Okay, so you can, this is only for one location. What you can do, you can get this data set and this data set into your CAD software. At the first plane, you twist it by 40 degree. Last plane, you twist it by this degree, and then you create a solid, what you call loft, and that will create your blade. Okay, so this is the simplest way of doing the design. Okay, how do you know it's optimized? How do you know it is optimized design? It's actually not an optimized design. Why? Because this formula I used, this formula is approximate formula. This is not the 100% correct formula. It's a, I can say there is a first design. Okay, this formula for the twist angle is approximation. This equation for C is approximation. It's not the correct formula. Correct formula, you have to do lot of iteration. Okay, and this formula again, A and A star, A prime is approximation. You have to do lot of iteration. That's why you need software. What software we talked about? Q Blade or Herb OPT. Okay, so this will start off with a nice design, but this is not give you the maximum efficiency of what we are looking for is I think 0.4382, but actually you will not achieve that. Maybe 0.3 you will achieve, because these are approximate formula. Okay, that's fine. Then you can change the twist angle a little bit. You can change the chord size. You can do a lot of things in CFD simulation to come up with optimized blade design. Okay, or use that sophisticated software, Herb or Q Blade, to design it. But this Excel spreadsheet will help you to design the process. Okay, if you go one step further and you want to visualize that, then I will tell you to use this one. I will leave it to you. Okay, I will ask Professor Siban to distribute this file to you, so you can play at your own time and design a blade. Okay, so I have shown you before. Now I am going to show you in details what you need to do. Okay, if you don't know the Python software code, it doesn't matter. It's very simple code. It's actually everything is written here. So this is the diameter. R is 1 meter. Okay, you can make it 2 meter. You can make it whatever length you want. I started with 1 meter. Density is 1000 and velocity is 2 meter. Our power, we need 5000 watt, means 5 kilowatt. Can you see it on the screen? 5000 watt. This one. CP value, we are expecting 0.4. The design may give you 0.4, may not give you 0.4. Your tip speed ratio is 4, blade number is 3, and optimum angle of attack is 5 if the blade is not rotating. If the blade is rotating, then you need to twist the blade. Then you calculate rotor sweep area, okay, from the value of R. Then you calculate omega, rotational speed in radial per second, from the value of lambda. How much is the rotational speed? Then you calculate torque based on the power. So now you divide that section into 10. You can divide the section into 20 also, but 10. Then you define each radius length. Here is the important, interesting parameter. There is you can control the hub width. How much is the optimum hub? Does anybody know how much is the optimum hub? So you don't start the blade from the radius 0. You start the blade, you have a structure, then you put the blade on a hub. And there is a ratio between hub diameter or hub radius to the blade radius. How much is that? 0.2, 0.3, 0.4. I will play with that, yeah? Okay. This is what you can control here, this line here. Then it calculates chord length and twist length based on your lift coefficient and drag coefficient. And what type of turbine we are using? These are the, again, simplified formula. It's not the optimized formula. It's a simplified formula, twist angle. And what was, okay. And we are using aerofoil S822. If you want to use another aerofoil, you have to get the value of XC and YC and type it here. If you want to change the aerofoil structure, design, you just take the value and put it here. It's available in different websites. You just change this parameter here. What else is there to change? No, these are just for plotting. Okay. Plotting. Okay. So let's give it a run and see what happens. Okay. Give it a run. What happened? So it creates 4 graphs. First graph show you your radius and your twist chord length. Your chord length, when the radius is small, chord length is large, 0.35 meter. And as you go along, your chord length comes down to very small. Twist angle is important parameter. At the beginning, your twist angle is 22, 23 degree, and it drops gradually to a very small value. And if you want to look at physically, all the blade, 10 blade, at different plane, this, the first one is the big one is at the front, the next one is a plot in 2D. It doesn't make sense. So let's look at a 3D, and you can see how the blade shape is. You can see the blade shape. You can, each of these plane, you can put it in a CAD sheet, and then you can loft it, it will be added. So you see that twist angle and things like that. Now I change it to, what happens? This is the hub. So I want to optimize the hub. What is the appropriate hub? So I put the number to 0.1 and run it again to see what's the impact of hub. Oh, look at the graph here. It's over twisted, first one. Then came back. Then profile is very complex in the beginning. And you see the twist angle of the first blade is very high, almost 50, 60, yeah. So you don't need to have a small hub. Okay, I make it even smaller. .05. That means there is no hub. You start the blade, 3 blade connected each other. Okay, so what happens? You see the blade, first blade, where is that? Angle, twist angle. First blade twist angle is 80, 90 degree. And is, so this type of twist, massive twist you need, and you don't get a good profile. And you can see the front one is almost very narrow, needle-like. So it's not a good design, right? You cannot manufacture either. So you need to have a nice hub. So let's make the hub. What's the optimum hub? Anybody knows? 50% is it? Or 20%? So let's do 40%. I will come to, okay, to help you, let's go to, did I close my PowerPoint slide? Yeah. Okay, there is a hub here, right? So I put a 50% hub, I think, 40% hub. And then run the blade design again. Now you can have a nice smooth blade and things like that. Okay, so that is hub is very important, and you can optimize little bit of blade design by playing with this hub that we didn't discuss before. So you need to have a middle hub part, then you grow the blade from here. You don't grow the blade from the center line of the turbine. Yeah, you need to have a optimized hub, and that looks nice. You can play with velocity here. You can play with the radius here, how big you want, and TP speed ratio is another important parameter. Let's make it 1 TP speed ratio and see what happens. Okay, so TP speed ratio 1, blade design completely changes. You don't get a TP speed ratio of 1 actually. The axial, you see the blade design, is a different blade design you are getting when you have a TP speed ratio of 1. But you don't have TP speed ratio of 1. It's not very efficient for this type of blade. TP speed ratio 1 is for Savonius type axial design, vertical design. For axial design, TP speed ratio is about 6 actually is the best one, 6 or 7, something like that. And so you run it again. And you get a different type of design, very big, and you need it very strong at the beginning because you're dealing with water, very big at the root, and then it comes down to very small. Okay, so you can see the parameter changing, your parameter here on the software, you can design your blade. And this is a simple software, and it's for free because I wrote it and I will give you. Yeah, you can play it there, you design it. At the end of the day, I request you make a turbine by wood or 3D printing and then put it in water and see how it works. But this tool will help you to design this blade shape and things like that by changing your TP speed ratio here and by changing what else, your radius here, your power output, CP value, this velocity V. If you want more velocity, you can change that. Let's see, 3. Yeah, it changed the blade design again. Yeah, so you can use this. I think rotor diameter is one of the important parameter also. So you can change it to 0.8. You calculated a rotor design, right? Can you tell me the number? Maybe 1, right? How much? 0.9. 0.9, 1 actually. So if you run it here again, yeah, this is the design of the blade you get. And lambda, this tip speed ratio has a big impact on the shape and the design. For a water turbine, we need a very thick blade at the root. Air turbine is different. Wind turbine is different. But for water turbine, we need a very thick root in the thick blade in the root because we need to have a strong, and then gradually comes down. Yeah. So this is the design. Tip, again, lambda has a very big impact on how you design the blade. You change the lambda, you get a different shape. Very important parameter, lambda, tip speed ratio. How you change the profile. Okay. So this code I will request Sivan to share with. I think all the lecture note will be shared with you. So you will have that, and without having very complex, sophisticated software, you can use a simple Python to design your blade, and you can graphically see what is the blade shape and structure, and you can play with that. Is that okay? Okay. And also Excel spreadsheet, if you want to go in a lower level calculation, then we have Excel spreadsheet also. But Python is self-explanatory. It's not very difficult software. Everything is written on the right hand side. You just make changes here and you get your blade design. Okay. Thanks for your attention.